Hello students, welcome to design of steel structure. In our last video lecture, we have completed the point number 8, up to point number 8. Okay, so till point number 8, we have found is how to choose the desired section, how to find the desired section for particular amount of compression load, and also to check whether this section is sufficient to carry that particular load or not. So after finalizing this section, our next step is to place these two sections in a particular spacing. That means what would be the spacing of these two sections. So how can we find this spacing? So for that you have to go to this point number 4. So in point number 4 it is mentioned that ry you have to place in such a way that new ry becomes more or equal to rz, which I have described in my previous video lecture. Okay, that means the moment of inertia about this y-axis should be at least equal to moment of inertia about z-axis. So in such a way we should place this channel sections or two sections. Okay, so from that you can find the spacing of these two channel sections. So this is one section, this is one section, so this is the spacing between these two sections. So this spacing can be found by this by equating this moment of inertia of y and z axis. Okay, so now next is have to design this lacing. So it is guided that the lacing should be placed at a spacing at an angle of 40 degree to 70 degree with the vertical axis. So generally 45 degree is selected or is best suited. Okay, and then after that you have to satisfy this condition. That means the spacing of this lacing bar A1 by Ry should not be greater than 50 or 0.7 times the slenderness ratio of the member as a whole. So what is A1 by Ry? So that is I described it previously. So this is the A1. So between this is one point and this is another point. So this vertical distance between these 2 points, okay, is called the A1. So you have to fulfill this criteria. That means point number 9. So A1 by Ry should not be greater than 50. Okay, so you can find this A1 from the geometry of this lacing bar. Okay, so let us draw this uh, here. So suppose, okay, I have drawn it in the next page. Let us go back to the page. So here, so when you find this spacing between these two channel section, that means you know this spacing. Okay, so this is capital S. Okay, and the distance from this point, okay, this point to this bolt line, okay, that means this distance is called G and small g, and it is found in the steel table. In the steel table you can find this G, where it is found somewhere this G star. Look at this G star. So you can see this channel section. So we need spacing, this spacing, that means this spacing where bolt is placed, because you see this is the channel section, this is one leg, this wave, and this is flange part. So in flange there is a point, that is this point. Okay, here the bolt should be connected. So from that point, so this point to this point is called G. Okay, and this is mentioned here in the steel table. Okay, now let us go to the steps, design steps. Okay, where here, so this part you can find from the steel table. This you have to find, this is the spacing between these two channels, that is S. S can be found by the equating the moment of inertia, and this side also that will be G. Now we need to find this A1. Okay, so we can draw a triangle like this. Okay, bigger triangle, and you can divide this triangle by making a horizontal line here. So this point from this bolt to this line, okay, this is a1 by 2. Okay, so if you see this angle, this angle is theta. Okay, so theta, and this is 90 minus theta. Okay, so this is 90 minus theta. So you see this is a1 by 2, a1 by 2, and this is 90 minus theta. So how can we find this a1 by 2? Because you know this spacing from this point to this point, right? That is s plus g plus g. So if you take tan theta, okay, tan theta here, so tan 90 minus theta, so tan 90 minus theta will be equal to how much? Height by base, so a1 by 2 by this total from this point to this point, that is s plus 2g, right? So you have found this s, you can find this g. So from this equation you can find this a1, total a1. Okay, so this a1 is basically from this bolt to this bolt. Okay, this bolt to this bolt, so you can find this a1. Okay, so now what is the steps? Let's go to the steps. Sorry, so here you can see this a1 by ry should be not more than 50 and 0.7 times the slenderness ratio of the member as a whole. So you can find the slenderness ratio of the member as a whole. Okay, so the total slenderness ratio of a member as a whole will be total effective length, that is KL, by the least radius of gyration. So that in that radius of gyration you should use RZ, because whenever you will place these two sections to make this built up section, this then RZ will be the minimum one. So in case of finding the slenderness ratio of a whole member, okay, built up member, you have to use the RZ, not RY. Okay, because radius of gyration has changed, because you are considering the total uh, member or the total assembly. So in that assembly rz will be the minimum one. Okay, so you have increased the ry. So then so you can check this condition, point number 9. So if it fails you should change the angle of the lacing bar. So you have to change this angle 45 degree. And what you can do, you can change the spacing also, or you can increase the spacing, because the spacing is the minimum spacing. Okay, so you have to modify that. Generally it will be satisfied. Okay, if you take 45-degree angle. Now we have to design the lacing bar. So how can we design this lacing bar? So that for that there is a guideline in IS 800. That means whenever you have to design this lacing bar, so it will be designed as a structural member, because this lacing bar will be carrying some compressive load. Okay, so let us go to this IS 800. So here you can read this point number 7.6.6.1. So this point, so the lacing shall be proportion to register total transverse shear of Vt at any point in the member, equal to at least 2.5% of the axial force in the member, and shall be divided equally among all transverse lacing system. Okay, what it means? It means, okay, the picture is here, you can see. So you have to place these two channel section like this, okay, back to back, and the lacing will be provided on this surface, on this surfaces here and here. And the lacing will look like this on the two planes, on this side and on this side. Okay, now what this clause is saying, it is saying that a transverse load of 2.5% of the axial load will act in this direction. That means this column will be subjected to a load of P, okay, and this transverse load will be 2.5% of this P, okay, and this load will be shared by this plane and this plane, okay. So because this plane and this plane are parallel, so in between these two planes, this transverse shear will be shared equally or divided equally, okay. So 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 the load which will be shared by this plane or panel, okay, that will be acting on the lacing system, okay, in this lacing system, and this load will create some component along this lacing bar. You have to find this component of this transverse load, okay. So that means a load of uh, this load will act on this direction, okay, this direction, and this load will create some component along these directions. You have to find this component because this load or this component will be a compressive load for this lacing bar. So this lacing bar should be designed for that compressive load, because if it fails, the total assembly will not be together, because you should connect these two channel sections by this lacing bar. So in connecting these two channel sections, it will be carrying some compressive load that will be found by this 7 clause number, this 7.6.6.1. And if the lacing fails, so it cannot bind these two channel sections, so it should be sufficient strong, it should be strong enough to carry this compressive load, okay. Now, so what will be that compressive load? So for that, let me erase this first, okay. So here you can see this load is coming on this lacing, and you have to find the component along this direction, okay. So what you can do, you can, so let me take this line diagram here, okay. So here you can see this load is Vt by n, this is Vt by n, okay, Vt by n. So this load is Vt by n, same, and we don't know this force. How can you find this force? So let us say that this force is Vc, Vcl, you can write it Vcl, okay, Vcl, okay, let me write it clearly, Vcl, okay. So you have to find this Vcl. So what we can do, we know this angle, that is 90 minus theta, okay. So the component, that means we are doing the back calculation basically, okay. So v component of this Vcl along this direction is equal to how much? So it will be Vcl cos, or you can write, you can, if you take this angle theta, so this component will be sin theta. So let us directly write this sin theta, okay, because this angle is for theta. So the component which is perpendicular, okay, or which is not making the angle, that is sine component. So Vcl sin theta is equal to this component, okay, this component, that is equal to Vt by n, okay. So in this equation, if you can find this VCL now. So VCL is equal to Vt by n into cosec theta. Okay, so you can see it. So this component is equal to Vt by n cosec theta, and this component is also Vt by n cosec theta. Okay, so this is clear. Okay, so do not engage your mind in this simple thing. So this is simply you have to remember this: the compressive load along this lacing bar will be Vt by n cosec theta. Okay, then so you know this, the total compression which is coming on the lacing bar now, and you have to check whether this lacing bar, what should be the thickness of the lacing bar, what should be the width of this lacing bar. Okay, so that it can carry this amount of compressive load. Okay, so here initially it is assumed that the lacing flat is safe, and then we will check whether it is safe or not. Okay, so this is the step number 12. I have described this 11 number, okay, in the picture, and you can read it. You have the PDF. Okay, then what will be the width of this lacing bar? So it is mentioned here. The diameter, first of all, the diameter of the rivet or bolt is assumed. So because to connect this lacing bar with the channel sections, you have to assume a particular amount per diameter of the bolt. Okay, so if so in that case you know the diameter of the bolt. Now if you know the diameter of the bolt, the minimum flat width should not be less than 3 times the nominal diameter of the bolt. End connector is nothing but the bolt. So if the diameter of bolt you have chosen, that is 16, then the minimum width is should be 3 into 16, that means 48. If it is 20 millimeter bolt, then it should be 60 millimeter width. Okay, then thickness, the lacing, if a single lacing system is adopted, the thickness T of lacing flat should not be less than 1 by 40th of this effective length. Okay, for double lacing system, the thickness T of the lacing flat should not be less than 1 by 60th of this lacing effective length. Okay, now you have to find the effective length of the lacing bar. Okay, and then I'll uh, explain it. Okay, but let us read this point 13. So minimum radius of gyration of the for the lacing flat is computed, that is R minimum is equal to T by 12. So from this line you have to find the thickness, and from point number 13 you have to find the minimum radius of gyration. And if you know the radius of gyration, okay, that means you know the effective length of this lacing bar, you know this radius of gyration, you can find the slenderness ratio, and also if it is a rectangular section, then you can find the buckling class. Then using the proper uh, table, you can find the design compressive strength of the lacing bar. Okay, and by multiplying with area, okay, with the design compressive stress, you can find the design capacity of the lacing bar. It should be more than this Vt by n cosec theta. Okay, that means capacity of this lacing bar to carry the compression should be more than this Vt by n cosec theta. Okay, so now let us uh, find this effective length of the lacing bar. So here same thing you have to do from this triangle. Okay, so on this triangle, uh, this angle is theta, so this angle is also theta, and you have to find this distance from this point to this point. So this angle is theta also, so this is height. Okay, now because this will be height of this triangle and this will be hypotenuse. Okay, so from this triangle you can find this sine theta is equal to height by hypotenuse, that is this effective length of this lacing bar. So you know this distance, that is s plus 2g. Okay, s plus 2g by this effective length is equal to sine theta, sine 45 degree. Okay, so you can find this effective length, that is equal to s plus 2g cosec theta. Simple. So after finding this effective length, the thickness t of the lacing bar should not be less than, so it should be more than 1 by 40 of the effective length. So you can find the 1 by 40 into the effective length, and the thickness, you assume a thickness higher than that. Okay, then for a single lacing system, and for double lacing system it should be 1 by 60. Okay, then the radius of gyration for the lacing flat should be t by root 12. Okay, so you can find this thickness from this solution. Okay, and then r minimum is equal to this thickness by root 12. Okay, so then I have to check the slenderness ratio of the lacing bar is computed, which should be less than 145. So the slenderness ratio of the lacing bar should be less than 145. You have to check, because you know this radius of gyration of the lacing bar and you know the effective length. You can find this. Okay, it should be less than 145. After that, uh, in a riveted and bolted construction, effective length of the lacing bar is the length between the inner end bolts, which I have described, and 0.7 times the distance between the double lacing system. So in case of double lacing system, it should be 0.7 times the distance of the, that means what we have found, it should be multiplied with 0.7 for the double lacing system. Okay, so you read it, point number 14 is very clear, you can understand that. Okay, then uh, read this point number 15. So design compressive strength of the lacing flat is computed for the calculated value of the slenderness ratio of the lacing flat. This should be more than the force in the flat. So how can you find the design compressive strength of the lacing flat? So you know this effective length of the lacing flat with what we have found now, just now, then by this r minimum. Okay, that is t by root 12. Okay, so you can find this KL by r minimum, and you can go to the IS 800. Here you can see, for this type of section, this is because this is a flat plate, so section will be this section, so buckling class will be C, and then you should go to the table 9C. Okay, so table 9C, buckling class C. So if for particular value, for this value KL by R minimum, you will get a definite value, and for that value and this 250 grade, okay, you have to find the FCD, design compressive stress. Okay, you know this, how can find, how can we find this design compressive stress? So I will not describe it here. Then so it means, so you will get the design compressive stress, and you have to multiply with the area, so that you will get the design compressive load or load carrying capacity of the lacing bar. So it should be more than this Vt by n cosec theta. Okay, very simple. So here the design of lacing bar is completed, but the numerical or total quotient is not completed, because you have to also, you have to design the bolt connection or rivet connection, because you have to connect this lacing with the channel by a bolt or by a rivet. So you have to design this rivet, because to design this rivet or bolt, you have to find the force which is coming on the bolt on, and also you have to find the bearing capacity of the bolt and shearing capacity of the bolt, and then you have to finalize this design. Okay, so this is up to the lacing design, and in the next video lecture we will solve, or we will understand this design of the connection. Okay, and then we will explain the we will understand this batten design. So what is batten? So batten is basically which is provided at the bottom. I mean, if you see the picture here, you can see this is a batten. Okay, so batten is provided in the intermediate height, so somewhere it is provided at the bottom, you see here. Okay, so you have to design this batten also. and also you have to find this thickness, width, and these connections. Okay, so in the third part of this built up column we'll complete that part. Okay, so I hope you have understood, and I will recommend you to rewind this video lecture, and because if you don't understand this theoretical concept, you cannot find this solution for the numerical. Okay, so thank you very much.